I will do that, okay? What I'll do is I'll make a video, and the video will be I'll have a screen. It says Unit 1, or I'll say Atomic Theory Test, IB, whatever, and I'll do a review. Clear? I'll go through the chapter, I'll have the test in front of me, give you some hints, good, on what to know, etc. Okay? Now, are there any questions? I need something specific about atomic theory, about the book. Don't just come up with some random things. Give me something to work on here. Anybody? Nobody? Nothing? No? It's very straightforward. It's very straightforward. What are the name of the lines in the excitation of the hydrogen atom relative to spectral analysis? Yes?
Balmer series?
Is it the Palmer series, would you say?
Balmer.
I need a name.
The Balmer series.
How do you spell that?
B-A-L-M-E-R.
B-A,
L-M-E-R.
the Balmer series. And how many lines do you get, basically? Yeah, now, this is something you should be on the tip of your tongue, right? I mean, this is something you need to know. Yes, Munkel, you remember?
5.
Yeah, you get 5 lines, 5 spectral lines. And what is special about this particular series? Anything?
They're visible.
What is it?
Visible.
It's visible. It's in the visible spectrum. And why don't we do that? Why don't we do this for sodium? Why don't we do it for sodium? We do it for hydrogen, and it works, yeah? The model works. And we're actually using sort of like the Bohr model, aren't we? Yes? Because what we're doing is, we're saying that hydrogen, this is the 1s electron, correct? And when we excite it, we're exciting it up to many shells. Yes? Up to many shells. And then what's going to happen is, that's going to give off, what kind of energy does it actually give off? Electromagnetic radiation. Yeah, that's correct. Very good. And what kinds of electromagnetic radiation is it going to give off? We already said visible is visible light. Light that you see is visible. It's electromagnetic radiation. What other kind of light is it going to give off?
Ultraviolet light.
Ultraviolet light. What series is that called?
It's on the first Lyman series.
The Lyman series? How do you spell that?
L-Y-M-A-N.
Lyman. And that series is going to give you...
There's no A after the...
There's no A? Excellent. You'll never know if I made the mistake on purpose or to see if you're listening. You'll never know. Okay. So what kind of light is that giving off? Ultraviolet light. That's right. That's right. Very good. Okay. Anything else on the hydrogen spectrum? Oh, you didn't answer my question. Why don't, we do it for hydrogen. Why don't we do it for sodium? Professor Ringo. Yes.
Sodium has a lot more electrons.
Sodium has a lot more electrons. What does that have to do with it?
It might be a lot more complicated.
It's a lot more complicated to the point where, what?
You can't really know which electron moves to which energy.
Well, what happens to the Bohr model when you apply it to a more complex atom? What happens to it?
It doesn't work because...
It doesn't work? That's putting it mildly, isn't it? It degenerates and decays the whole model into oblivion, doesn't it? It's just too complex. Yes, Munkle? You're the one that presented it. Would you say that's correct? The model doesn't just fall apart, it vaporizes. Yes? So we need something else, don't we? We need another model. Who's the dude who came up with the other model?
Heisenberg?
Was it Heisenberg?
Schrödinger?
Who was it? Schrodinger came up with a model that makes a little bit more sense. And how that model works is extremely complex. It's for another day. If you major in chemistry, if you major in inorganic chemistry, if you study in graduate school the D subshells, you'll get into it. But it's extremely complex, extremely complex. Understanding the hydrogen is enough at this level. Yes? It's enough. But how do we know what is a outward sign that, and you may not know the answer to this because we don't have the lab set up and we have to do this. We're going to actually do this lab, but what's an outward sign that we need a model because we need a model? We need one. We need one. When I energize hydrogen, I can get colors, correct? Yes. When I burn copper, anybody know the color I get?
You get sort of a bluish green.
Yeah, green. Yeah, really a green. If you want to say bluish green, I'd say a mint green, if you want to be specific about it. Bluish green would be more of an aqua color, more of a cyan color, I think. But maybe I'm wrong. But, it's green. It's certainly a leprechaun green, an Irish green, yes? So you get a color, don't you? You get a color. So something's happening, isn't it? Something's happening with the excitation. I can put this wave of energy, I can flood the atom with the copper with this wave of energy. And the electrons are going to go wild, aren't they? But they're going to go wild in a chaotic, but really a pre-designed way that's going to be predictable, definable, and something that's expected. And they're going to absorb whatever energy it needs, and most of the energy will pass by. But when it de-excites, when it falls down to a more stable level, it will give off these little packets of energy that it absorbed. And what are these little packets of energy called? Singular. What is it? A quantum. Yeah. Quantum theory. Okay. I'm going to show a film. We got to kind of get a little bit more past. We got to catch up a little bit, but I want to show a film on quantum theory. It's kind of cool, actually. If you follow quantum theory out to its limits, it's pretty weird stuff. But what's the one thing it does relative to disciplines within chemistry and other sciences? What's something that the quantum theory does? It gives a connection between what two disciplines within science?
Physics and chemistry.
Yeah, physics and chemistry. It kind of like bonds it and supports it. If you're a chemist, there's that interchangeableness. Because chemistry really is the study of what?
Atoms?
Not atoms, but...
Elements.
Not elements, but... What is that mostly made of?
Space.
Empty space. And what's touching my head?
Empty space.
No. Well, empty space, yeah, but yes.
Oh, stretching.
Just stretching, okay.
Protons?
No.
Molecules.
No.
Subatomic particles.
No.
Surface?
The valence electrons, right? Aren't the valence electrons the ones that are really touching my head? It really doesn't hurt much.
Yes,
Okay.
but wouldn't the protons in your base and the protons in the book be the ones that are repelling each other?
Maybe, but can't the electrons in my head and the electrons in the book repel each other too?
Fair enough.
Okay. But it's the outer. It's the outer. It's the outer. It's the outer electrons that are actually, the valence electrons that are actually touching. So when chemistry is really the study of the interaction among and between valence electrons of elements, different elements, like the valence electrons of hydrogen compared to the valence electrons of chlorine. That's really what chemistry is the study of. What's physics the study of? And you get new molecules, right? You get new molecules. Well, what's physics the study of?
Physical matters.
The physical world. So don't electrons give off energies and they stay those and they go right back to the same element? So I can excite hydrogen and then it de-excites and still hydrogen. I can excite copper and it still stays as copper. So there's no changes, there's no new properties, there's no new compounds, right? So can't that be physics? Of course it can be. Yes? Yes, absolutely. So there's a connection. That quantum theory gives us a connection. Anything else? Is that enough? Or you got to know. Make sure you know the ionization energies and different parts of the ionization energy graph. Like why are there peaks? Yes. Why are the peaks of period 1 and 2, the max points, are they higher or lower than the max peaks of, let's say, period 3 and 4? What happens to that? What happens to the peaks of, in other words, what happens to the peaks of what are the max peaks really in each period? If you look at an ionization energy chart, what are the max peaks? What are they? The maximums, what are they? They're what? Come on, guys. You should know this. This is... They're the noble gases, right? Aren't they?
Yes.
They're the noble gases. So, what has a higher ionization energy? The noble gas of helium or the noble gas of argon?
Helium.
Helium. So those max peaks kind of decrease, don't they? Why is that? Why are the D subshell ionization energies flat compared to the S and the P's? Why are the F's even flatter? Why do you get those? Why is the ionization energy less than the ionization energy of why is the ionization energy of aluminum less than that of magnesium? Yes?
Because it loses electrons to become more like the nearest noble gas.
No.
Because the smaller the shell energy level, it's more stable. Like S is more stable than P.
S is more stable than P. In other words, what's that law that says you put electrons in starting with the lower energy and going to the higher energy? What's that rule? Do you remember?
I think it's Aufbau principle.
The Aufbau, and state the Aufbau principle for me.
Electrons are placed into orbitals of the lowest energy first.
Of the lowest energy first. So is that electron that's going into 3s, 3p1 higher energy or lower energy than 3s2? It's a higher energy, isn't it? Isn't it? Mm-hmm. So is it going to be easier to remove?
Yeah.
Yeah, absolutely. But is the 3p2 at basically the same level as the 3p1?
Yeah.
Yeah, absolutely. So you get that, increase again. You get that dip because the 3S is, the 3P1 is going into a higher energy according to Aufbau, correct? You get it? Am I being clear? Okay, good. So let's quit this. Make sure you know every peak and valley, every flat area. Make sure you can interpret an ionization energy graph like Johnny B. Good plays the guitar, sitting under that tree as the train passes by. And the conductor says, "Who is that sitting under that tree, playing that guitar like he's ringing a bell?" Got it? They're looking at me like I'm crazy. But they may be correct, but I'm not wrong. Got it? Okay.